So from last time, we were talking about this continuity for functions of more than one variable. And we also discussed how polynomials are continuous on all of Rn, as well as having rational functions kind of in the shape of having a polynomial in the numerator and a polynomial in the denominator is continuous everywhere except where the denominator is equal to 0. So we're actually going to start today's lecture with an example where we're going to utilize this. So we're going to show that the function that's piecewise defined as 2x over y and x squared plus y squared, wherever the point x and y is not equal to 0, 0, and it's 0 when we're at this point. So we're going to show that it's continuous everywhere. Except the origin. So the first part of this statement is relatively easy because we can just cite that this is a rational function. So because this is a rational function, a polynomial over a polynomial, everywhere except for the origin, we know that it's continuous everywhere except where the denominator is equal to 0. But that doesn't mean that the function f is not continuous there. We just know that this is discontinuous at 0, but guess what? It doesn't include 0, 0, the origin here. We have this point at 0, 0. So it could be that this rational function has a limit of 0 as it approaches 0, 0, meaning that we filled in that hole and f is continuous everywhere. But we're going to try to show that the limit of this guy, this rational function, does not have a limit of 0. Or at least that the limit doesn't exist. So let's kind of put that into words. So the rational function to xy over x squared plus y squared is continuous at least everywhere that the denominator x squared plus y squared does not equal 0. So this leaves us to prove the limit of xy going to 0, 0 of f of xy, which is the limit as xy goes to 0, 0 of the rational function 2xy over x squared plus y squared does not equal 0. That will make sure that this is not a continuous function because the limit does not equal what the function is at that point. Okay. So last time we did this by trying to look at different paths, right? So it's really easy to disprove or sorry, in other words, it's easy to prove that a limit doesn't exist by taking two paths. So that's kind of what I'm thinking here. We are trying to show that the limit doesn't equal 0 or perhaps doesn't exist. So why don't we start with two paths? If we take the path, and I'm going to do something similar to last time, where I have y is equal to mx, where m is some real number. So this is an infinite number of paths here. I'm going to plug that in. So I look at 2xy over x squared plus y squared, and I'm evaluating this with y is equal to mx. So I go ahead and plug in an mx every single time I see a y. So then I get a 2mx times an x, and then I get x squared plus 2, that is a 3, 2m, oh no, mx squared. There we go. So this is equal to 2mx squared all over a x squared plus an m squared x squared. So notice that I have x squared in both terms of my denominator. I can factor that out. And I also have this x squared in the numerator. So this simplifies really nicely to 2m over 1 plus m squared. Now remember, m was any real number, so I could make this some other, if I chose m is equal to 1, I would get a very different value if I chose m is equal to 2. But notice that they both of those paths still pass through the origin, 0, 0. So from this, I can say that the limit as xy goes to 0, 0 of 2xy x squared plus y squared along the path y is equal to mx is is equal to the limit of this evaluation when y is equal to mx, but we know that to just be the constant 2m over m plus, or 1 plus m squared. So this limit doesn't really do anything. It's still 2m over 1 plus m squared, with m being any real number. So if I chose a slightly different m, meaning I took a different path, I get a different limit. So that means that the limit doesn't exist. I get different values along different paths. So thus, the limit does not exist, which means that our function f of xy is not continuous at the origin, 0, 0. Question, why do we choose the path based on the point xy is approaching in the limit? Oh, do we choose the path based on the point? Yeah. So in this example, we were looking at the limit going to 0, 0, right? I need to choose the path so that it includes that point, right? So think of it as the path at which you're approaching that point from, right? So if this was a different point, say maybe 1, 1, I would have to change the path that I would take, because it wouldn't include, well, this one would include 1, 1 as long as m is 1. But you can choose different paths, just make sure that all of those paths pass through the limit point, right? that's the whole idea, is we're taking these paths to get to this point. So our path should definitely include that point. I think there's a question on the homework that is similar to this, but you have different points other than 0, 0. Okay, so now functions of 3 or more variables. So the definitions of limits and continuity should say are mostly the same. So if f is defined on a subset D of Rn, so we're in n-dimensional space. So f is input is n variables. Then the limit, and we write it a little bit differently. And it's just a notation to help us deal with, we don't know how long these x's are because we're in Rn. So we can also write this as kind of like this limit for these vector formulations. So f can be input a vector where all of the elements of it are the scalars like x, y, z, and so on, right? So this is a compact way of writing such a thing. This means that for every number epsilon that's positive, there is a delta that's positive such that if x is in our region D, and the distance from x to x naught is less than delta, then my function has a distance away from L that is less than epsilon. So this is just extending that epsilon delta kind of formulation that we used previously, but for functions of arbitrary number of variables. The function f is continuous at x naught if I have that the limit as x goes to x naught of f of x is equal to f of x naught. So another property that we utilize with limits, and we've learned this in Calc 1, is if we know a function to be continuous and we're taking the limit of it, we can move the limit inside of it. All right, so we're going to have to utilize that for our next example here. We're going to find the limit as x, y, and z goes to 1, -1, -1 of arctan of x plus y plus z. So we know arctangent is a continuous function, right? If that's the case, then we can move the limit inside of it because we know that the limit of a continuous function is just that, that function at the limit point. So we can write the limit as x, y, and z approaching 1, -1, -1 of arctan of x plus y plus z is equal to arctan, the limit as x, y, z goes to 1, -1, -1 of x plus y plus z. And that limit's pretty easy to do. We know this is a polynomial, so it's continuous everywhere. So we are allowed to just plug in those points. So this is arctan of 1, -1, -1. Or just arctan of -1, which is -pi/4. So the premise of a function being continuous in higher dimensions is still very similar, right? If I know a function to be continuous, like arctangent, or maybe sine, cosine, e to the x, right? If we have these functions that we know are continuous, we can kind of extend that logic to functions of higher variables. Since I knew arctangent is a continuous function, I'm able to move the limit inside of it because I know that the limit of this continuous function is the function evaluated at the limit point. So I keep that logic up, I bring it inside. This is a continuous function as well, so I'm able to just plug in those points, and then I just evaluate. Okay, we're going to do one more example for this section. So we're going to use the epsilon delta definition to do the limit as x and y goes to the origin 0, 0 of x squared y and x squared plus y squared. So we were able to disprove that a limit exists or prove that it doesn't exist by choosing two different paths. However, if we can't fill in a hole or we can't do it either doing some other kind of limit trick, we have to use this epsilon and delta definition to do the limits. And you won't have to do that too often in this class. Most of the problems will be kind of rigged so that you can either fill in holes or yada yada, but you need to be able to kind of know that this method exists. It's a little bit harder, but it is worth seeing it at least once. So we're going to do the epsilon delta definition for this. So first, I need to get an idea of what the limit point might be. So we're going to let x equal y. So we're going along this path. So the limit of x, y going to 0, 0, and I'm plugging in x is equal to y. So every time I'm actually going to do, every time there's a y, I'm going to put an x. So this is x cubed and x squared plus x squared. So this is the limit as x, y goes to 0, 0 of 1/2 x, which is equal to 0. Now, I want to stress that this does not mean the limit is equal to 0. This says that the limit along the path x is equal to y is 0. I did this because I need at least a starting guess to figure out what the limit point might be. So this is a perfect candidate, right? It's either 0 along every path or the limit doesn't exist. Okay, so this does not prove that our L or limit point is equal to 0, but we have a guess now. Okay, so now comes the hard work. So we have epsilon be greater than 0. We're going to find a delta such that if the distance, and actually let me write it like this first, because we're doing it like x minus x naught, which in this case is x minus 0, because it's the origin, plus y minus 0 squared. So we write this as just x squared plus y squared. So if this quantity is less than delta, then the distance between my function x squared over y, x squared plus y squared, to the limit point, which I believe is 0, is less than epsilon. So note that x squared is less than or equal to x squared plus y squared. This implies that 1 over x squared is greater than or equal to 1 over x squared plus y squared, which means that x squared over y, or sorry, x squared times y over x squared should be greater than or equal to x squared times y over x squared plus y squared. Now, we have these x squareds here, so we can cancel them. So we can say that the absolute value of y is then greater than or equal to x squared times y over x squared plus y squared. In fact, this should have absolute values as well because we multiply it by this y quantity, which might be negative. So it's just a simple logic train where we started with x squared, and we said that if we add a positive thing, or at least a non-negative thing, it's definitely greater than or equal to it. We flip them. So we have 1 over x squared is greater than or equal to 1 over x squared plus y squared. We multiplied by x squared times y, where this might be a negative number, so we have to group it into absolute values to maintain our greater than or equal to. And then we just canceled these x squareds. So now we're at the point that the absolute value of y is greater than or equal to our function. So our function, the distance to what we suspect is the limit point, which is 0, by this definition, this is less than or equal to the absolute value of y, which is equal to the square root of y squared, which is certainly less than or equal to the square root of x squared plus y squared, which is strictly less than delta. So that means if we choose delta is equal to epsilon, then our function and the distance to what we suspect is the limit point is less than epsilon. And there we have it. That means we've proved that the limit point is in fact 0. So let's kind of go through this again and kind of talk our way through it. The idea here was we needed to find a delta such that if we had this property, if we had the delta was greater than our x squared plus y squared, then it implied that the distance to our limit point was less than epsilon. So the idea is we're trying to find delta such that this is true, right? So there's going to be a correlation between delta and epsilon, right? So the idea is we're keeping as epsilon, but we're trying to find a delta such that this implies this. So we go through, we're trying to show that we can write some kind of relationship between our limit point and delta, because then we can just pick delta. If we let delta be epsilon, that means that this is implied, which means that our limit point must then be 0. It is, seeing it for the first time, if you haven't seen it in Calc 1 or something like that, might be a tough pill to swallow. It is the formal way of doing limits. Everything else that we've kind of learned are doing tricks. But this is the real math way of doing limits, is we have to find a delta such that it implies that the distance from our limit point is less than some epsilon. Okay, so you've seen it once. You're probably not going to have to do it maybe once in this course. But I just want you guys to kind of see this formal definition here. Limits are hard. And this general process has to change for what your function is, right? So notice that all the steps that we took earlier here were very particular to the function that we were working with. Will this process be on exams? I think this is much too hard of a question to put on an exam. I just want you guys to see it, because this is limits. This is how you do limits. So if you're an engineer or maybe a chemist or a physicist or what have you, and you have to do this limit and none of the tricks that you've seen before work, you have to do it this way. But I think this process needs a lot of practice. And I think it's much too hard for an exam question. I think this showed up once in the past on the exams that might be on the exam archive. And I think students did very poorly on that question because you need a lot of practice for this. Okay, so with that ends 11.2. Let's go ahead and jump to a new page. And we'll start talking about 11.3. So 11.3. Okay, we're finally getting to the core of Calc 3 here. We're trying to get to real calculus in higher dimensions. We're going to be talking about partial derivatives. So let's consider a function of f of x and y, of course, of two variables, if we set y equal to b, some constant, then what we have is a function of one variable that relies on x solely, right? Because b is now this constant. Now, you can argue that we can manipulate b, but it's always along the line y is equal to b. So we can redefine g in that case, right? But if I consider b to be this constant, this is a function of only one variable, which I'll call g in this case. Where g of x is now a function of one variable. Well, let's take a look at G prime at some point A. So I'm looking at the derivative of G. This is, by definition, the limit as H goes to 0 of G of A plus H minus G of A all over H. But we've defined G to be the function f of x and y, where y is equal to b. So we can sub that in here. This is the limit as h goes to 0 of f of a plus h b minus f at ab all over h. We call this f, and this is a subscript of x at the point A and B. This is known as the partial derivative of f with respect to x. At the point A, B. So similarly, we can say that f sub y at the point A, B is the limit as h goes to 0 of f of A, B plus h minus f at A, B divided by h. This is the partial derivative of f with respect to y. At the point AB. So this AB is actually just these dummy variables. So we can actually write down the definition for all x and y, where we have the partial derivative of f with respect to x is the limit as h goes to 0 of f of x plus h y minus f of x y all over h, and then f y, so our partial derivative with respect to y, at xy is the limit as h goes to 0 of f of x y plus h minus f at x y all over h. And we'll talk about what this kind of means in a second. Let's talk about some notations. Do not want a straight line. So one way might it be just to drop the arguments of x and y. You're just saying this is the partial derivative with respect to x. Another way to write this is these script d's like this. So instead of having like this derivative, say like this, written like this with these d's, these are partials. So this is partial f, partial x. Another way to write this, and this is less common, but you may see it, is write a capital D with respect to x of f. So this is some differential operator with respect to x acting on f. And of course, we can do this as well for the partial derivative with respect to y. So we could write this as f partial y. We could say this is partial f, partial y, or some differential operator with respect to y acting on f. I think these first three are the most common that you'll see. Okay, why don't we take our 5-minute break there, and then we'll come back and we'll talk more about these partial derivatives. Okay, so let's get started again. So we're going to talk about the interpretation in just a little bit, but first I want to talk about the process to find these partial derivatives. So the main idea here is when we're taking partial derivatives, what we're going to do is consider all other variables a constant. So let's do some examples. Let's see what these partial derivatives in action. So we're going to do straight lines, not straight lines. There we go. We're going to find the partial x derivative of f, as well as the partial y derivative of f at the point for -3, when our function of x and y is equal to x squared plus 3x times y plus y minus 1. So before we find it at that point, let's go ahead and actually find what the partial derivative with respect to x is everywhere. So this is the partial derivative, and it acts just like derivatives that you're used to from Calc 1, whereas if we're like looking at this addition, we can apply it to each one of these separately. So we can look at the derivative of the first term, then the partial x derivative of the next term, and so on. So we'll have the partial derivative with respect to x of y minus the partial derivative with respect to x of 1. So let's look at each one of these separately. So remember, we're keeping y a constant here, right? So whenever we're taking a partial derivative, all other variables are considered constants. So I'm looking at this first term. Luckily, I don't see any y's. So this acts just like a normal derivative, which is 2x. So I move on to my next term here. I get 3x times y. So y here is considered a constant. So you can think of the coefficient out in front of x to be 3y. So if I take a derivative of that, I just get 3y. Now I move on to this next term here. And remember, we're considering y to be a constant. So that means that I just get 0 here. There are no x's in this expression. And then finally, the same thing comes to this constant here. This just this 1. This is also just minus 0. So this is just equal to 2x plus 3y. So now let's go ahead, and before we plug in points, let's do the other one. Let's look at the y partial derivative. So this is partial y of x squared plus partial y of 3x times y plus partial y of y minus partial y of 1. So we go through these once again, but now I'm considering x to be a constant. So I take a look at this first expression here. I get x squared. I have no y's. So this means that this is a constant with respect to y. So I just get 0. I move on to the next term here. I do have a y, and I have x being this constant, so the coefficient out in front of y can be viewed as 3x. So I go ahead and take a derivative, and I'll just get 3x. I move on to the next term here. I do have a y, and the coefficient is just 1. I get plus 1. And then I have this constant 1 here at the end, so I take a derivative, and I get 0. So here we just have 3x plus 1. Okay, so now we are asked to find both of those derivatives at the point for, what did I say? For -3. Oh, it's supposed to be a 5. Okay. Not that big of a deal. We haven't plugged in 3 yet. But it's supposed to be a 5. There we go. Okay, so now that we know what the partial derivatives are, we can find fx for -5. So this was 2 times x, so we plug in a 4 there, plus 3 times y, so we'll plug in a -5. So this just gives us -7. Now f sub y, the partial derivative with respect to y at the point for -5. This was 3x plus 1, or 3 times 4 plus 1, which should just give me 13. So that was a pretty easy example. We're just doing it on these polynomial terms. Let's do some more examples. So this one's not a polynomial. we're going to find the partial derivative with respect to y when our function is y times sine of x times y. So partial f partial y is equal to the partial y derivative of our function y times sine of x, y. So we're going to use our normal derivative laws to kind of help us through this. So notice I have a function of y, this just y, and then I have another function of y, sine of xy, and they're multiplied together. So this would be a product rule. So what we do is we have the derivative of the first times the second plus the first times the derivative of the second So here I just have 1, and then times my sine of x times y. Over here I have y times the derivative of sine, which will be a cosine of x times y. But let's not forget that we also have to take the derivative of what's inside. So we'll have partial y of the interior, which is just x times y. So this is equal to sine of x times y plus, now the derivative of this term here, remember x is just a constant in this regard, so this derivative will just be x. So we get x times y times cosine of x, y. And that's our derivative, right? So it might be helpful if you just kind of think of, x as this constant. Maybe you even want to just not look at it. Maybe you don't want to look at this x and you just set it equal to a, and then at the end of the day, you turn it back into an x. But that's exactly the process, right? X was a constant through this whole regard, and it was just doing derivatives with respect to y, like we've done in Calc 1. Okay, let's do one last example here. We're going to find the partial x derivative when our function is equal to 2 times y over y plus cosine of x. So we're taking a x derivative, so y is a constant in this regard. So fx is equal to our partial derivative of our function 2y over y plus cosine x. Okay, so it looks like the only instance that x shows up here is in the denominator. So we can use the quotient rule here. So the quotient rule, I'm going to write out the denominator first. It's the original denominator squared. So we'll have a 1 plus cosine of x squared. Then in our numerator, we have low d high, so this is the bottom, times the derivative. Oh, shouldn't use, so partial derivative of the top, which was just 2y, minus high d low. So we have the top times the partial derivative of y plus cosine of x. A lot of brackets. So I still have my denominator, 1 over y plus cosine of x squared. And then I'm going to simplify my numerator here. So I still have my y plus cosine of x multiplied by the derivative of 2y, and this is derivative with respect to x. So y is a constant here. So this derivative is just 0. So times 0 minus 2y times the derivative of y plus cosine of x. So this is a constant with respect to x. So that's going to be a 0 when I take the derivative. And then I take the derivative of cosine of x with respect to x. So then I just get a negative sine of x for my derivative there. And we can end the brackets. So my final answer will be a 2y sine of x all over a y plus cosine of x squared. And that's how we do our partial derivative for that function. Okay, so now that we've gotten some practice with this partial derivative, right? We've done its definition, we've done some examples on how to actually conduct the derivatives by making sure that all of the other variables are considered constants. What is it? What is the interpretation? What are we doing here? Okay. All right, now for some text. We're going to imagine that z is equal to our function. So we input an x and y, and we get a scalar z. And before we learned that this creates some surface, right? In R3, I input x and y, and I generate some points in the scalar z, and then the collection of those points generates this surface. Okay. So that's just reiterating that it's a surface, but we talked about that. If we let y equal to b, where b is some real number, we see the trace of the surface at y is equal to b, right? So this creates a trace. We're cutting along the y equals b line, and we generate this trace, which should look like a function in R2, right? Where I input an x and I get a z value out of it, right? That's all that matters, because now y is equal to some constant b. So kind of using some reverse logic that we did before. So if we let g of x equal f of x at b, so this is now a function that details the trace of the function f at y is equal to b, then fx along this trace is equal to the limit as h goes to 0 of g of x plus h minus g at x over h, which we just define as g prime. This is the slope of the tangent line at x. Right? That's how we learned what derivatives were like. That's their interpretation from Calc 1. Now, since this function f of x at b is the trace along y is equal to b, this means that fx at xb is the slope of the tangent line at x along the trace y is equal to b. So kind of imagine, if you will, let's go ahead and draw maybe some domain. That doesn't need a perfect square, but we're looking at the function from above, so we don't actually get to see the elevation of the function. I just want to see this in the xy plane. So that's actually kind of right. Maybe that this is in the xy plane. And z is coming out towards us. So we might have a line where y is equal to b. So that means y is equal to b is some constant value, so we're going just across. So you can imagine that if we had maybe some surface that kind of looked maybe something like this along this trace, right? So this is when we sliced our function here at y equals b. At any given point, we could find the tangent line, right? But this also is the partial derivative with respect to x along that trace. But I can change b to maybe be at a different location. So maybe we'll say that this is b1. This is y is equal to maybe b2. And maybe my function looks a little bit different here when I slice it. Now at this same x location, I have a slightly different. It's still a function that we're used to in Calc 1 because we're slicing it. This is still only a function of one variable when we take it along this trace. And we can find the tangent line at any specific location with respect to x. But now what's happening is we're taking different slices, right? So it looks like the interpretation that we should make is that fx is the slope of the tangent line in the x direction. So similarly, we can make the same type of argument for f of y. And this is the slope of the tangent line in the y direction. Now, we've only been looking at functions of two variables, and then we're just having x and y, but partial derivatives can go beyond that. They can go to functions of arbitrary number of variables. So the definition of a derivative with respect to the ith variable, which we'll call xi, is equal to the limit as h goes to 0, 1 over h of f of x1 dot 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 xi minus 1 xi plus h xi plus 1 dot 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 until we get to xn minus the function at x1 dot 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 xi dot 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 and then xn. So basically, it's the same thing, except for the ith component, you have a plus h. Right? Very similar to what we were doing with x and y. In the x component, we had a plus h, or we had it in the y component, differentiating between the derivative with respect to x and the respect to y. Okay, so let's talk about higher derivatives. If we have that f is a function of two variables then f sub x and f sub y are as well, provided that they're differentiable. We'll talk about differentiality a little bit later. We can use partial differentiation on both fx and fy, because they themselves are functions of x and y. So imagine that we have the partial derivative of f with respect to x, and then I took another x derivative. We can write this as fxx, or we can write it as partial x of partial x of f, or we can write it as partial squared over partial x squared of f. So that's the second derivative with respect to x. We could also say that maybe we have fx, and now I take a y derivative. So I get fxy. So it's important to note the ordering here. Here, it means that I'm taking an x derivative first and then a y derivative. You can also write this as partial y of partial x acting on f. So again, we have the x derivative acting on f before we take the partial with respect to y. Or we could write this as partial squared partial y partial x on f. Now it's also worth noting the ordering of here in the denominator. Think of it as you're reading from right to left about what's acting on f. The partial x hits it first, and then the partial y hits it after, right? Similar to like how we wrote it here, right? The x hits it first, and then the y hits it after. So we could also have fy and then take an x derivative. So in this case, the y goes first and then x. So this is partial x of partial y of f, or partial squared partial x partial y of f, right? Because the y is sitting at first and then the x. And then finally, we can have both partials with respect to y, or fyy is equal to partial y partial y of f is equal to partial squared partial y squared f. Okay. So now we're going to introduce a really nice theorem for partial derivatives. So the theorem states if my partial derivatives fx with respect to, so f of x and y, and then I'm taking a derivative with respect to x and then y. And I also have my function, but now I've differentiated with respect to y and then x. If these are both continuous, on some region D, then I can say that the order of which I took my partial derivatives doesn't matter. As long as both of those derivatives are continuous. And this is a pretty nice thing because a lot of times we can look at a function and we can say, oh, this is a continuous function, and you know its derivatives ought to be continuous, right? So you look at maybe sine of x, right? You know the derivatives of that are going to be continuous, right? It's infinitely differentiable. You can take more and more and more and more derivatives, right? So same thing here. You can look at these functions and get an idea that, oh, these derivatives are going to be continuous. One way might be a lot harder than the other way to take the derivatives. So let's do an example of this. We're going to find w(yx) when w is a function of x and y, and it is equal to x times y plus e to the y all over y squared plus 1. So I look at this, and I know that this is certainly going to be a continuous function. And I have suspicions that this is going to be a continuous function when I differentiate. But let's go ahead and do it out. So we get w sub y. So we're doing the y derivative first. My first term will just give me an x, since an x is a constant. The second term I have to do the quotient rule for. So I get 1 over y squared plus 1 squared times low d high. So the derivative of e to the y is just e to the y. And then y squared plus 1 minus high d low. So you put e to the y, and then I take the derivative of the bottom here, which just gives me 2y. So this is equal to x plus, and I can factor out an e to the y squared plus 1 squared times a y squared minus 2y plus 1. Okay, so that was doing my whole y derivative, but I still need to find the x derivative after this. So I go ahead and I take the x derivative of the first term. I just get 1. And then the second term doesn't even have any x's in it. This is just a constant with respect to x. So this is just plus 0. Right? So my derivative with y and then x is just 1. Okay, let's do it the other way. if I look at Wx first, so I go back up to my function here, I look at my first term, right? This should just give me a y, and then my second term doesn't have any x's in it. So this is just equal to y, and then Wxy is equal to 1. So if I had my suspicions were correct that the derivative of this was going to be a continuous function, then I could have just done the opposite order of my differentiation and saved a lot of trouble taking this y derivative, because taking the y derivative of just y is a lot simpler. Okay. So we can apply the above theorem to higher derivatives as well. So we can apply this theorem to higher derivatives. Oh, we have a question. Is there an if and only if situation where you can say if then the derivatives are both continuous? No. If both of the partial derivatives, if the order for, if you say that Wxy is equal to Wyx, and theirs are equal, that doesn't mean that the derivatives are continuous. So it's not, yeah, it doesn't go both ways. There's actually a really nice property in the complex plane that does something similar to that, but we're not going to deal with that, but it's pretty cool. Okay, so doing it for higher derivatives. So for example, if I took x and then partial y, this is equal to f of y x y or f of y y x if, well, that's a terrible if these are all continuous. So no matter how many partial derivatives we're taking, we can always rearrange as long as they're all continuous. We have about 5 minutes left, and the next thing I was going to talk about was differentiability, which I think will take a little bit longer than that. So we're going to end it there for today.